Hi everyone, my name is Uri Klarman and I'm the CEO and co-founder of bloXroute Labs. And today we'll be speaking about how blockchains work and how to scale them. So the agenda for today is first bloXroute who. I'm going to tell you about who we are, what we do. Then we'll go to blockchains 101. If you don't know anything about blockchains, that's perfectly fine. We'll take it from the start. And then we'll talk about the scalability problem, considered by most as the #1 problem of blockchains. How do we move blockchains from processing 3 or 5 or 10 transactions per second to process thousands or tens of thousands or hundreds of thousands of transactions per second? And lastly, we'll talk about the bloXroute design. What's our solution and what's our approach to solve the scalability problem? And then lastly, we'll wrap it up with some Q&A. So, bloXroute who? bloXroute was founded by crypto and networking experts from Cornell and Northwestern University. So I myself am a computer network researcher at Northwestern, and my co-founders are Professor Emin Gun-Sirer, so Gun, the leading crypto expert at Cornell, also co-directing IC3, Professor Kuzmanovic at Northwestern University, who's a net neutrality expert. So he's on the steering committee of Google's MLab for net neutrality. He received the NSF award for net neutrality, these kind of things. And Soumya Basu, the creator of the Falcon network, which is a relay network used in Bitcoin and Bitcoin Cash today. And together, we built bloXroute, which is a scalability infrastructure which allows blockchain to scale. But let's start with blockchains 101. I'm going to talk about Bitcoin because Bitcoin is the first blockchain and it's still the golden standard. All other blockchains out there are doing a variation of what Bitcoin is doing. But if you understand Bitcoin, then you understand blockchains and you understand the principles of blockchains. And the goal of Bitcoin is simple. The goal is to cut out middlemen from financial activity or transactions. So Bitcoin aims to be this money that is as easy to use as credit cards, but without paying 3% out of every transaction to the credit card companies. And it aims to be as safe as a bank, but without every person in the world having to have an account with a bank. So how does it work? Well, let's consider Alice, who wants to buy an apple from Bob. Well, every Bitcoin user has a wallet. And a wallet really has two pieces, a public key or a public address. And earlier, Amy said, OK, she explained the difference between the two. But for now, we'll consider them a single thing. So the public address is a way for me saying, oh, this is me. If you want to send me money, send it to this public address. And if I want to send money to you, I'll send Bitcoin from my public address to your public address. The public key, the private key, is a way of proving that you are the owner of the public key. So let's go back to Alice and Bob. Alice wants to buy an apple. Bob gives her the apple, and Alice now has to pay for it. So she creates a transaction. And in the transaction, she writes, take 1 Bitcoin from Alice's public key and send it to Bob's public key. And she signs it with her private key to prove that she's actually the owner of Alice's public key, where the money is taken from. Once she creates this transaction, she propagates it to the entire Bitcoin peer-to-peer network. So she tells it to her peers, who tell it to their peers, who tell it to their peers, until it reaches everybody on the network. The size of the transaction, by the way, is a few hundred bytes. In the Bitcoin peer-to-peer network, there are special nodes called miners. Miners listen to these transactions coming from all directions, and they try to aggregate them into blocks. So a block is really just a header with a lot of transactions in it. And the reason that they do that is not because they're really nice. It's not because they like Alice or they know Alice. The reason they do that is that each block created rewards its miner with Bitcoins. So that's their business. Okay? They listen to transactions, and they turn them into blocks because this is how they make money. And the process of it is the following. So they listen to all these transactions coming from everywhere, and they turn them into a block. And then they hash the transactions together along with an arbitrary value called the nonce. And if the result of that hashing is smaller than some target, then the miner successfully mined a new valid block. But the chances of that really happening is very, very, very small. So what happens in reality is that miner try one value, and then another, and another, and another. And each miner is trying as many values as he can, as fast as he can, as he competes with the other miners in who will mine the next block and get that reward. Once, at some point, some miner will find a nonce that the hashing of it gives a small enough value, and he mined a valid block. Once that happens, he sends it to everybody else in the network, similar to how the transactions are propagated, and all the miners will hear about it and move to compete who's going to be who will mine the next block. So what's the outcome of all this process that I just described to you? Well, first of all, the result of it is that all the transactions ever to happen, the entire history of transactions in Bitcoin, is held in a chain of blocks. This is the blockchain. Now, if a transaction is included in the blockchain, then it actually happened. And if a transaction is not in the blockchain, then it didn't happen, or it didn't happen yet. So the blockchain not only holds and stores the transaction that happened, it defines what happened and what didn't happen. So the blockchain really is what defines if a transaction took place or it didn't. An important thing to note is that when that hashing that I told you about, that the miner takes the transaction, hash them, and that arbitrary value, the nonce, he also includes there the hashing of the previous block. And why is he doing that? He's doing that so if an attacker, okay, he comes and he says, I want to change or alter the history of transaction. I want to change something that happened in the past. I paid Chris over here some Bitcoins, and I want to undo it to still have that money. Then he will have to go to that block and either add or remove a transaction, but he's going to change that block. That changes the hashing of that block, right? As soon as you change it in any way, its hash changes. So the attacker will have to revalidate, do that work, try values until it's valid again. But more important than that, he will have to then go and revalidate all the consecutive blocks afterwards, because each one depends on the one before it. If you change one, you also invalidate the one after it, and after it, and after it, and after it. Now here's the real kicker. Okay, now to the real security model of blockchains. That for the attacker to succeed, he will have to do that, right? Revalidate the block and everything else, while everybody else are making the blockchain, the original true blockchain, longer and longer. So for the attacker to succeed, he will have to be stronger, faster, with more hashing power, with more computation power than everybody else combined. Okay, so for the attacker to work, it's called the 51% attack. He will have to have majority of hashing power. But if hashing power is decentralized, if no entity has the majority of hashing power, then the blockchain is secure. The data there is immutable. One more term that I would like to bring up here, which we'll revisit later, is the term fork. A fork is what happens when two miners mine a new block at approximately the same time. So one miner mines block A on one side of the network, and approximately at the same time, another miner mines another block, block B, which gives him money rather than the other guy. And now you have this ambiguity. Which block is really the tip of the blockchain? Is that A or B? But that ambiguity is naturally resolved when the next block is mined. So if the next block is mined on top of block A, this is now the longest blockchain. And everybody who's following the blockchain who believes B will orphan it and move to this blockchain. And if the next block is on top of block B, then everybody will orphan block A and will continue on the side of the fork of block B. Now, what are blockchains good for? What are they useful for? So let's start, when aren't they useful? They're not useful if you can trust. If you can trust your bank to move money from account A to account B, you don't need a blockchain, okay? A single server will be a lot more efficient than doing something on a blockchain. If you can trust, if you want immutable data and you can trust a server, oh, store that data for me, and you know he's going to store it, he's never going to crash, he's never going to change it, he's never going to be hacked, then you don't need a blockchain. Because, well, you gave it to him, and he's not changing it, it's immutable. But when is it useful? It's useful if you want to have direct interaction without a middleman. So Alice and Bob were able to trade, although neither of them have a bank account. Neither of them is holding a credit, is working with a credit card company. So that's one thing. Another thing is immutable data. A lot of the time, having immutable data is important, but it's not that easy to guarantee. But if something goes on the blockchain and decentralized, then it doesn't matter if somebody tried to change it in one server, because as a whole, there is a consensus that everybody knows, oh, this is the true data. Nobody can go back and change some record in one way or another, because it's immutable. And lastly, or not really lastly, because there are another million things you could do with the blockchain, but these are kind of like the principles, visibility. If you're trying to fight corruption, for example, then you could say, oh, if I could track every dollar that the government is spending, where is it going to? And where is it going from there and there and there? So this is the complete opposite of anonymity. If you could do that, then you have visibility. And visibility could be useful for a lot of things, okay? Pharmaceutical companies can use that because they want to track all the ingredients in the manufacturing process to make sure nothing is fraud, nothing is fake, et cetera. That's useful for a bunch of things. So that was blockchains 101. You guys now know how generally a blockchain work, and who are the actors, how do they behave, what's their incentives, et cetera. So Bitcoin is great. It's really great. It's awesome, okay? It is. But Bitcoin produces 1 megabyte block of transaction every 10 minutes. Now, the average transaction size in Bitcoin today is 540 bytes. So on average, the Bitcoin blockchain processes something like 1,900 transactions every 10 minutes, or roughly 3 transactions per second. If you think about other blockchains out there, they're doing a similar thing. They're doing 5, they're doing 7, they're doing 10 transactions per second. But if you think about all the cool things that you want to do with blockchains and crypto, those are at a completely different scale. So credit card companies today process 5,000 transactions per second on average. That means they have much higher peaks. Vending, if you wanted to use Bitcoin, for example, or blockchain for vending machine, just vending machine, around the globe, and each vending machine sold 4 items a day, you'll need 1,000 transactions per second just for vending machines. And if you want to do really cool stuff, okay, autonomous swarm robots communicating trustlessly over the blockchain, that's 50,000 transactions per second. If you want to do the global micropayments or micropayments at a global scale, which is when you don't need to pay the credit cards 15 cents plus 3 transactions, you could do all sorts of cool business models that can do very, very small payments, 1 cent, 3 cents, half a cent. Well, that's 70,000 transactions per second, or roughly. And for the real heavy lifting, if you want to do social media on a blockchain, so Twitter on a blockchain, like memo.cash is doing today, or a Facebook on a blockchain, if every active Facebook user would do just 4 likes a day, that's 200,000 transactions per second. Okay, so the numbers that we need are, the scalability is like nowhere close to what Bitcoin can do today. But if we want to do more transactions per second, how can we do that? Well, we can do one of 2 things. We can increase the block size, right? If we move from 1 megabyte block to 10 megabyte blocks, there's 10 times more room there. We'll move from 3 to 30 transactions per second. Or rather than mining a new block every 10 minutes, you can mine a new block every minute. So again, you get the same 10x improvement there. Changing these parameters give exactly the same result, as I'll show you in a few minutes. So I'm going to talk about the block size because it's easier to follow, but then we'll go back and say, oh, why it's exactly the same. So let's say that we want to increase the block size by a factor of 10. What happens then? Well, first of all, great. We just moved from 3 to 30 transactions per second. But every time now that a node has to send a block to another node on the peer-to-peer network, now he has to send, rather than sending 1 megabyte, he has to send 10 megabytes. And that's going to take him 10 times longer at the best case scenario. Okay, I'm ignoring congestion, I'm ignoring topology inefficiency, lost messages, a bunch of stuff, not even talking about filtering and throttling and these kind of stuff. Best case scenario, everything is fine. Well, 10 times more data takes 10 times longer. If you think about the network as a whole, the time it takes for a block to reach the entire network also increase by the same factor. And that had been actually shown empirically that that's what happened. There is linearity there. Why do we care? Because that time it takes for a block to reach the entire network, that is the window of opportunity in which forks happen. Okay? A fork can naturally happen only if I mine a new block, despite another one already mined, but I didn't hear about it in time. It's still propagating, and I had extra time, and now I found it, and now we have a fork. So the probability for a fork increases by roughly the same 10x. Okay, it's going to increase by 10x, at least until that probability is very, very close to 1. So we're going to have 10 times more forks. That is annoying for all sorts of reasons, but it's still OK. The system still works. Okay, we said that forks are something that can naturally be resolved, so we'll have more forks, and we'll solve them. No problem. But what happens when we move beyond that, from 1 megabyte to 100 megabytes? So we moved from 3 to 300 transactions per second, which is still nothing close to what we want and need. Well, at that point, the propagation time, for the time it takes for a block to reach the entire network, becomes so long that it exceeds the time between blocks, the 10 minutes that Bitcoin gives between blocks. And what that means is that you're going to see a fork happening pretty much every time a block is mined. And what happened then to the blockchain is that it unravels like a rope. So you have forks, and then forks of forks, and forks of forks of forks, and nobody knows which fork to follow anymore. Nobody knows what is the truth anymore, and the blockchain breaks. This is the scalability problem. And now something that is not in my presentation, but everybody, at least in the crypto and blockchain space, they know about and of the scalability problem, but nobody talks about what's causing it. Well, now you know. That's what's causing it. So we said earlier that we can increase the block size or change the time between blocks. Well, I'll tell you this. The probability of a fork is something like 1 minus e to the power of blah, blah, blah. And then it really depends on the ratio between the block propagation time, the time it takes for a block to reach everyone, and the time between blocks. So it doesn't matter if you increase the block size and therefore the time it takes for a block to propagate, or reduce the time between blocks, the result is the same. So it doesn't matter which parameter you play, the result is exactly the same. If you try to increase it by 2 orders of magnitude, everything breaks. I want to add one more thing about it. Everything I'm describing now coming from the world of Bitcoin. Okay? It's a permissionless blockchain. And some of you might be familiar with permission blockchain. So rather than everyone can participate in it, you have something like, oh, I have a node in my, my company office in Europe, and we have another node in the US and one in Japan. Okay? So it's a closed system. Do they have the same problem? Well, they do. IBM/Hyperledger, the guys there who are doing permission blockchain, they go to their customer and say, oh, you can do great stuff with us, but if you want scalability, you have to run your nodes in the same data center. Because if everything runs in the same data center, then you have no problems. Everything is super fast, and everything works. But if those customers of them try to deploy it in the wild, in their own infrastructure, they get exactly the same problem. Now, it's funny because Some of their customers are banks, and banks have a regulatory problem there. They're not allowed to run their nodes on somebody else's infrastructure. They have to run it on their own infrastructure. So it applies to all blockchains. So we said all of that, and this is really a networking problem, right? It's about how we move data around. But sending a lot of data to a lot of people is a solved problem, okay? Akamai solved it in the late 90s. We really know how to do that. So YouTube, Netflix, WeChat, they send terabytes of data to billions of people. Nobody blinks an eye, right? We all use YouTube all the time. Like, what's the problem there? We really know how to send a lot of data to a lot of people. So there is a solution that helps with this block propagation and data propagation. It's called relay networks, right? You deploy a network of servers that are highly connected to each other, and if I mine a block, I send it to the relay network, and it broadcasts it to everybody else around the world really fast. That really helps with the propagation of information. The first relay network was deployed in 2015, and if you look on stats about Bitcoin today, you will see that a block 1 megabyte block takes something like 10 seconds to reach the entire network. If you look at more historical data from 2013, 2014, you will see it takes 30 seconds or 50 seconds for smaller blocks to reach that. So relay networks really help with a problem. You could say that they solve it. But there is a problem if the Bitcoin protocol or the blockchain protocol rely on a relay network to scale. Okay? Because if everybody rely on the relay network, then the relay network has the power to do pretty much everything that it wants. So if I'm the relay network and there is a guy I really don't like somewhere and he's a miner, I can say, well, you know what? I'm not going to relay his block. Whenever he mines a block, I'm going to ignore it. Now, if Bitcoin, for this example, scales and he's doing 1 gigabyte blocks or something like that every minute, then at that scale, it's not like that miner can just propagate it the regular way over to peer-to-peer, right? It's too slow. We just established that, right? They have to use the relay network. And the relay network can do awful stuff. They can reject people. Or if I really like someone, I'll send him the block first so he have extra time to do mining, okay? So that's money in the pocket for miners. So that's, I have a microphone in my pocket. A third thing, the most awful thing that the relay network could do, they can actually ban wallets from participating. So the relay network, even if they're really nice people, the NSA can come knocking on the door with a list saying, oh, these addresses are suspect of terrorism acts. So you're not allowed to relay any block that contain them. So the relay network will reject such blocks. And again, they can't propagate in any other way. So if the protocol depends on a relay network to scale, then everybody in the system have to place their trust in the relay network. And if the blockchain require everyone's trust to do anything, then what's the point of the blockchain, right? Just keep the bank in the middle. Everybody trusts the bank to move money between accounts. We just lost, what's the idea of a blockchain? In comes bloXroute. So bloXroute is and that's what we do. bloXroute is a blockchain distribution network, a BDN, okay? We do a similar thing. We deploy a network of servers around the world. But it's a new networking primitive. It's similar to Relay, but in addition to providing the performance, it's provably neutral. Now, what does it mean that it's provably neutral? I'll tell you how it works. If you guys run a Bitcoin node, I give you a small piece of open source code. I give it to you. That's your magic gateway. Change nothing in what you do, but run this code on the same machine that you run your node and add it as another peer. So if your node is connected to this peer and this peer and that peer, add this magic gateway, and it's just like any other peer, only it sits on the same machine. But when you send a block to the magic gateway, he's sending it to everybody else 1,000 times faster than your other peers. And he's going to tell you about blocks 1,000 times faster than your other peers. So there are really two pieces to this. One of them is the performance. Oh, it's 1,000 times faster. I'm going to explain that, but let me start by saying this is nothing novel. Getting the performance is super easy. I said earlier, like sending a lot of data to a lot of people is a solved problem. Our real novelty is about neutrality, which I'll tell you right afterwards. So how do we get 1,000 times faster? Well, when you run your node and you mine a block and you give it to the magic gateway, it translates every 540-byte transaction into a 3 bytes ID. Just turn it into something much, much smaller. We internally send all of that, and we map it back to the transaction on the other side. And we can do that because we are a single entity. We're not a decentralized system. So this is really the simplest thing you can do. You can do better than that. You can do Bloom filters, IBLTs, these kind of stuff. But you get 2 orders of magnitude improvement just like that. Another thing that we do is cut-through routing. So when your magic gateway sends the block to the BDN, to the blockchain distribution network, then rather than wait until we receive it and then send it, we do cut-through routing or streaming. We receive it, and we start sending it as we receive it. So by the time the last packet arrived, everything else was already broadcasted. And just that last packet had to be sent. So that's another between 1 and 2 orders of magnitude. So we get more than 3 orders of magnitude, honestly, doing the simplest things out there. We can do much, much better, but we decided to start with simple and working at a scale that nobody is doing today, rather than, oh, let's jump to the complicated stuff for no good reason. Now for the real thing, OK? We're provably neutral, and this is how we do it. And this is our true novelty. What we do is the following. bloXroute is provably neutral because we prevent ourselves from knowing what's inside the block, where is it coming from, and where is it going to. So to prevent ourselves from knowing what's inside the block, then when you have a node, it gives the block to your magic gateway. It turns it from a giant block into something very, very small, and then it encrypts it. And it sends it through bloXroute encrypted, so we don't know what's in there. And only when your magic gateway hears from his peers, the other magic gateways, that they have received that encrypted block, then you send out the encryption key, both through bloXroute and on peer-to-peer, to reveal the content. So the content is revealed only when it's already too late to do anything about it. And even if we try to stop the key from propagating, it's a single small packet. It propagates very fast across the world. So this is really the key of what we do. We prevent ourselves from knowing what's inside the block until it's too late to do anything about it. To prevent ourselves from knowing where the block is coming from, magic gateways don't have to send the block directly to the relay to bloXroute, the blockchain distribution network. They can relay it through a peer. So similar to Tor, right? You send it to your peer who relays it to you. So if we are somehow forced to drop all blocks coming from North Korea, then North Korean nodes can send it through their European nodes or Australian nodes or American nodes, wherever. And when that's coming in, we have no idea what's in it or where is it coming from. And the same thing on the receiving end. So rather than receive directly a block from bloXroute, you can ask your peer to relay it to you. So you really don't have to interact directly with bloXroute to utilize it. And you get all the performance boost without losing the most important thing. Okay? You don't have to trust bloXroute because we have no idea where is it coming from, where is it going to, or what it contains. So that was the majority of what we do. I want to point out, just to give the full background of scaling, what are the other alternatives out there? So if you heard the term sharding, the idea of sharding is saying, well, blockchains don't scale, but how about rather than use one big blockchain, we use a lot of small blockchains and then somehow have them work and weave into each other so you keep the security part of it. It's a really cool idea. We're completely compatible with it, but it's sophisticated and complicated. It's really a hard problem. If someone in this crowd ever did a sharding to a database, and he knows how annoying that was, think about sharding a blockchain where everybody can try to attack it. It is really complicated. That is known as a layer 1 solution because it's on the layer of the blockchain. They're trying to make the blockchain better. Say, oh, let's not do one blockchain. Let's do several that weave into each other. Another solution, or two solutions, are layer 2 solutions. So Lightning Network and Plasma. The idea there is let's not put all transactions on the blockchain. If we want to transact, then we can open a channel between us. And then just every so often, we put it on the blockchain. So we create a contract where, oh, I put in 3 Bitcoins and you put 3 Bitcoins. And now if I want to pay you, I say, oh, now it owes you 4 and only 2 to me. So you can play and change the adjustment there. And the idea of the Lightning Network is that, oh, if I owe you 3 Bitcoins and you owe that guy 5 Bitcoins, then we can relay payments through each other. It's a super cool idea, but very hard to do, very complicated, and it's not entirely certain that it's possible to do, and it's actually useful for all the regular cases of just transacting. One more thing, if you ever heard about hashgraph or DAG in general, so directed acyclic graphs, it's the idea of rather than have a blockchain, which is kind of like a straight line of blocks of all the transaction, what if it grows in all directions, but we don't have any loops, so it's somehow OK? That's another interesting idea. It's possibly useful. It's possibly scalable. I'll say this. Somebody asked Goon not long ago, had someone seen that hashgraph is broken? And the answer is nobody had seen that it's broken, but nobody had seen it to scale too, right? It's kind of OK, it's promising. And even if it works, every node there has to communicate with all other nodes. That's the networking communication model. Okay, so everybody has to know everybody else. So we're fine with that as well. We're compatible with everything. That was bloXroute, and we'll just get to question, but I'll mention that we're hiring great people. So if you're looking to say, oh, I really want to move into the blockchain space, then reach out to me. We don't need blockchain developers, but we're always happy for great people. Questions? Oh, there's a microphone coming your way, Nathan.
How does this interact with other kinds of consensus mechanisms other than proof of work, like this one wasn't working?
No, it was working.
It's just
or maybe I'm very close to you, so I heard it.
Yeah, so how does this interact with other proof of stake style consensus mechanisms?
So just to give background to those who don't know, like the nitty-gritty details of blockchains, what we described here is a proof of work, right? Miners are working hard and trying these different values until every so often one of them succeeded. Proof of stake is saying, so rather than waste a lot of energy and electricity trying to do that, how about we give the vote and the right to mine to the next block according to how much of the crypto or the coin that you hold. Okay, so if you hold 10% of all the coins, then your chances of mining the next blocks are 10. And if you have 5, then 5. That's kind of like the idea. And to answer your question, what we do is working underneath the blockchain, right? It has nothing to do with what kind of consensus mechanism you have. What we do is to say, rather than sending your blocks through Comcast, who are A, slower than us, and B, they're actively filtering, throttling, and changing a bunch of stuff that you're doing. And you might be violating your contract by running a node to begin with. But rather, you can send it through us. We give you the same service, only 1,000 times faster, and we're neutral, unlike them. So it just works underneath it.
Can I ask a follow-up?
Sure.
So yeah, that makes sense, although you were talking about this ratio of the block propagation time versus basically the probability of forks goes to infinity at a certain ratio, right?
Or 1.
Or 1, yeah, 1. Yeah, can't go to infinity. But anyway.
You can if you want to.
So that's different in a proof of stake system, isn't it? Or is it not? Is it?
So it's not really about the proof of work or the consensus to that extent. It's about the fact that the bottleneck that's causing the scalability problem is how long it takes for the entire system to sync about a new block. And there had been work done, I think, by the Zerg, Andrew Stone, at Bitcoin Unlimited, that says, if you think about it, that the time dedicated to syncing to the entire system is time in which you can't create new blocks. Because if you create, you just create a problem, right? So if you increase that time, you reduce the time in which you can be productive. And the more transactions that you process, the larger blocks you do, that takes longer and important until it takes the entire time.
So my question is about the ID replacement. So it's really cool that you've come up with shorter IDs, but you're saying that you provide that censorship resistance by changing it to short IDs, encrypting the payload, and then sending it to the other side. But I need a lookup table as to rehydrating those IDs. How do I guarantee you don't give me bad addresses back when I'm actually reconstructing the block?
So that's a great question, and I'll try to answer it shortly without going into all the small details, and we can follow up later. But the idea is but it is a great question. So we have a single component that's doing that mapping, okay? Because we want consistent mapping across everyone. We send that mapping outwards. And the question is, well, can't that be, if you don't map an ID, can't that be used to censor a transaction? And that's absolutely correct. So I'll have to say two things. I'll start by saying that, one, not all transactions have to be mapped. Okay? There is some ratio of them that are going to, but you can always put transactions that weren't, just not too many of them. So we can only abuse it to some extent. Okay? So the idea is that if we want, we can either prevent everyone from using it, and that goes into another direction, or everyone fairly. Now, just an important thing that I didn't got a lot into is that we have no control over it. Well, I sent encrypted data, so I don't know any of it. But those that have the power are actually the magic gateways that run at the client. So what we're doing is really reversing the direction of the trust. We put our system intentionally at the mercy of the magic gateways. It's robust enough to withstand it, but the idea is that these rules of how many transactions, oh, you can't have too many which are not IDs, we don't do that. That's not in our control. It's done by the magic gateways, which are open source, run by the client. We have no say in that, and they can tweak it if they want to. There are some details about that, but that will require like a longer conversation.
Hey, Uri, so I'm sure I kind of agree with your approach here, but just to play devil's advocate, I'm sure you know there are people who don't. And so there's this kind of view that, like, you're talking about block propagation as like the primary kind of bottleneck, and other people would say that in order for the network to retain useful properties like decentralization and censorship resistance, that you need people running these nodes on, like, let's say home computers on their home setup. And so, like, at the scales you're talking about, people aren't going to be doing that. So I guess your thoughts on that and how that affects the network and scalability.
So that question or comment has two parts, which are both important. First, I want to emphasize that there is a question. Should just miners run nodes, or should every user run like a non-mining node to make sure he knows what's happening, etc.? But I want to emphasize that if the question was about, oh, do you need these non-mining nodes or not, and this wasn't the bottleneck, then you would see some blockchains trying to do 300 megabyte blocks every 10 seconds, and some who would say, no, we should stick with 1 megabyte block every 10 minutes because we care about these non-mining nodes. But we don't see that diversity of approaches because that's not the bottleneck. So there is a reason that even the biggest maximalists, they don't say, oh, let's do 300 megabyte blocks every 10 seconds, because they know intuitively that there is a problem, but it's almost never being put down like, okay, what exactly is the problem? Now, going back to oh, but what about these nodes? Then, first of all, we have been testing it using the Bitcoin Unlimited code base, the guys there who is one of the development teams of Bitcoin Cash. They were wondering how much transaction per second they can do. So they took the code and they started doing that. They found a very big bottleneck at taking transactions, putting them in the mempool. I won't get into the details, but it was something done single-threaded, so they had to parallel that, etc. We have tested, and we know that on a regular, like, a consumer-grade machine, like you have like a 2-core or 4-core, one of them, but like a regular one, you can process thousands of transactions per second. And if you prune the data, then you could, even the storage, which I don't think is an issue, but you can reduce it significantly even further. Now, I want to emphasize that what we do is solve the bottleneck. What blockchains should do with that, that's their decision. Do they want to do very large blocks at very short intervals, or medium-sized blocks at very short, whatever, that's their choice. That we have no say in that, and we support everyone. Like our idea is we're enablers. We're not trying to do our own thing. We try to help everybody else in this space. So to your question, I have my own personal opinion on that, but as bloXroute, maybe you're right. Maybe the other guy's right. Both of you should try, and one of you will be better than the other and will get more traction and will help more people to create real value in the real world and will stay. And the other will vanish because he doesn't make sense. Does that answer the question?
Hi. With so many parties needing to know about the transaction, are there any privacy concerns?
So that goes, yes, it's always true. So there are several systems out there. I presented Bitcoin because it's kind of like, again, the golden standard. That's kind of like the basis of it. But you have new things coming out like Monero or Zcash, which are privacy coins, where you see something and you can say that it's valid, but you don't know what's in there. You don't know what was sent from who to who and how much. Is that valuable? Some people would say it is. I think it is to some extent. Some people say it isn't. Can that be incorporated into Bitcoin so you can have like privacy transactions in the regular blockchain, or you need a different blockchain for that? I don't have the answer for that either. So it's definitely something important. And this space is moving in so many directions so fast that it's really hard to give a straight answer because like I don't know of everything that's happening. But privacy is a big thing. It's something important, and I can tell you that a lot of people care about it.
Thank you. Thanks for the presentation, by the way. Thanks. So a question I have about the release servers and the issues with censorship and that kind of thing. Wasn't that problem solved with miners as well? So in other words, if you pay the release server and you allow many release servers to show up, wouldn't you solve that problem?
So I'm not sure I understood the question. So could you?
Yeah, of course. So I was thinking the issue with the release servers is that you wouldn't have as many, and they would potentially decide what goes through and what doesn't, right? So if you start paying for that relay transaction, let's say, you would allow more relay servers to show up, and potentially with more relay servers, you get into the same kind of solution that we had for miners, right? Where you allow many miners to show up because you're paying them.
So you're absolutely correct, okay? So the idea is like, can you, the question was, can you pay a relay network and then you'll have a lot of relay networks and then you kind of solve the problem, right? You use just a relay network. So like all the questions here, it has several pieces and kind of different parts. So to an extent, you're right, but a lot of markets are kind of like in this scenario where you have a very strong networking effect, and this is also true here. The strongest relay network is going to be the most important, and then people would prefer it rather than using some second-grade network or something. And so it might end up not really solving it. If you have even a few large players can be affected by regulation. Okay, so we prevent ourselves from knowing what's in there, so we can't censor because, oh, I'm just moving data and I have no idea what's in there. If you have, let's say, 3 large players in there, can they or can't they be censored? Can they be affected by regulation in a few major countries? I'm not sure what the answer is. Maybe, maybe not. I can tell you this. If you use a single infrastructure, then you could be a lot faster than if you have several of them. Okay, if you have a single one and everyone are using a single mapping and they're using the same, it's a lot more cost effective. But maybe you're right, but up until now, we haven't seen such a thing happen. Okay. Also, another thing, it comes to, do you have to pay that relay network? Because if you do, that's a middleman, right? The entire idea was to get rid of them, right? So we put ourselves in a spot where nobody has to pay it to us, right? We do that. We have no idea what's in there. I can't charge you $5 a month to use a service because I can't prevent you from using me if you don't, right? I don't know where is it coming from. I don't know if it came from you, so I can't charge you for it.
Yeah, in that sense, you do pay for miners as well. So you kind of have that fee, let's say, in place. But I see your point. You could potentially have, let's say, a part of the network that is lower but free, and the other part is, super fast and paid, let's say.
So to an extent, you could say, oh, that's what bloXroute is doing, right? You could think of that. But we make sure we have a problem from our perspective to say, oh, you have to pay for it. That doesn't make sense. Nobody should use us if you have to pay us. It breaks the entire idea and the entire model, right? Because if you have to pay, then that means that someone can prevent you if you don't pay, right? And that's a bad idea. That's something that we try to solve.
And just one more follow-up. You said you improved 1,000 times, right? But that was 3 transactions per second, which means 3,000 transactions per second, which is still below the 5,000 from credit cards. What's your goal there? Do you
So as I said earlier, so this, really using the simplest techniques, gave 3 orders of magnitude improvement. We can do much better, okay? If you use, rather than send the IDs, you can say a Bloom filter of the IDs, which is going to add another order of magnitude improvement. You could use a combination of Bloom filters and IBLTs to reduce it even further. The last number, I don't know what it is. Like, I'm aiming to solve that, like, I want to do a Facebook on a blockchain thing, but just because I think it's cool. But like, my idea is that like, we should have more capacity than any application that want to use it. Okay, so like what's our end game? Now, we also can do software-defined networks, like a bunch of others, more sophisticated stuff. It's just like somewhere, it's a phase 2, some of them phase 3 kind of thing.
So, correct me if I'm wrong, but you said you start streaming the blocks before you've received the entire block, which means it's impossible for the relay nodes to be able to actually verify the blocks that they're sending are even valid. How do you prevent against denial of service attacks through the relay node where bad blocks are propagated fast to the whole network, actually blinding them from the correct data?
So that's a really important question. It has a phase 1 answer and a phase 2 answer. Phase 1, really practically talking, is that you can look in the proof of work or just the proof of stake. The first packet to come in, you can check it, and in the context of proof, you can see, oh, is the hashing there strong enough? Is it smaller than the target? If it is, then to make such an attack is as hard as creating a new valid block. So even if the rest of the block is invalid, it takes the entire network 10 minutes to create that as an attack. And worst case scenario, I send it to everyone. They don't trust me. They receive it and they verify. And if it's wrong, then they drop it. So that's a phase 1. I would like to remove even that because I don't want to see the proof of work. I want to hide it from myself. I don't want to know even that. Because you could think about, oh, if you, I don't know, some scenario where you think you know who that is and try to block him, et cetera. Phase 2, we want to do zero knowledge proof of kind of like, I can see that it's smaller than the target, but I don't see what it actually is. I can see that it's smaller than the target, but I can, oh, is that this exact number or is that exact number? But to make that right with without screwing it up somehow, we want like very deep peer-reviewed process. So it's kind of like a phase 2. It would require a bit of research and a bit of work to make sure we do it right. You'll have to yell.
The amount of compute power required at a miner's level to scale, is that going to be a limiting factor in the overall scalability of blockchain?
So if I understand you correctly, what you're saying is, I don't think it's the networking. It's about how much hashing power the miners have.
Correct.
Well, the amount of the hashing that the miners are doing is kind of like they take all the transactions, they hash them together, and then they try different values to see until the result is smaller than the target. And that the target adjusts every so often, so it stays at every 10 minutes. That has nothing to do with how many transactions are in the block. So the miner creates the block, he chooses the transaction, then he creates like a hash of all of it, and then it hashes that thing with the nonce, and then we try to do that. So it really isn't about that. You could argue, oh, maybe you need a lot of computational power in order to process a lot of transactions, but we have already seen that very like consumer-grade computers can do that at thousands of transactions per second. We don't know where exactly the line is, but it doesn't seem to be close to be the problem. It's like orders of magnitude better than the other stuff. Does that answer the question?
It does.
Thank you. Well, thank you, everyone. That was fun for me. I hope it was fun for you as well.